And here is a circuit. Here is an AND gate. You have to make sure that you draw your gates carefully so you can make a distinction between AND gates and OR gates. Otherwise that can get a little confusing. I remember back when I was a student, we were required to use templates. Do they still use those gate templates in electrical engineering? I guess people have stopped using them. And actually, I remember in one of my professors, he had a wooden templates for the blackboard. So you put this wooden template and then you would nicely draw those AND gates and OR gates. But apparently that didn't caught on because I think they were rather big wooden things for the board. So as long as you can see, I guess this AND gate looks a little too small, but probably doesn't matter too much. Let's give these lines some names. How about A, B, C, D, E? These are the primary inputs. And notice that here, lines G and H I guess I need to revise it. I should have said all branches of fan-out points. Sorry about that. All branches of fan-out points. So G and H. So these are two branches of this fan-out point. And let me give all the lines some names. Here is I, let me call this J, and here is K, and let me call this M. So I have a name for all the lines. Okay. So how many nodes we have? We start out with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we start with 12 nodes. So unless we do something, we are going to need 24 faults, right? Which include stuck at 0 and stuck at 1. So any node could be stuck at 0 or could be stuck at 1, right? Now let us see, can we reduce this 24 faults? Let us use this theorem, checkpoints. So what are the checkpoints? So checkpoints are all primary inputs, A, B, C, D, E, all branches of fan-out points, G and H. So these are the checkpoints, right? A, B, C, D, E, all primary inputs, and all branches of the fan-out points, G and H. So here we have a total of how many? 5 and 2, 7. So here we have a total of 7 multiplied by 2, that is 14 faults. So with 14 faults, these 40, if you test for these 14 faults, you will test for all of them. Now if you think about this circuit, you can actually reduce 14 faults to even smaller number. So for example, stuck at 0 here, stuck at 0 here. So we have 2 of them included in those 14 faults. But notice that stuck at 0 here and stuck at 0 here, they are equivalent, right? So you can even make this less. So you can do even better than 14. You can even reduce it further. But then as you keep reducing it further, you will need to think more and more intelligently. So you need to look at the circuits, maybe think about it, analyze it, and you can reduce it to lower number. But reducing it to 14 is straightforward. From 24 to 14, you simply use the checkpoints. So if you test with checkpoints, you will have tested for all stuck at faults. Any questions on this? Okay, so next let us consider test set reduction. Let us say that you have a set of tests. Maybe you generated them randomly, which is quite common. Now, if you have generated a set of tests, it is possible that you don't need all the tests. In fact, it's quite likely. Notice that it is common that one test for multiple faults. This is a very important fact to note. Also true for software. And I can give you an example. Let us consider this example. And for convenience, I will assume that this is fan-out free. So there is no reconvergent fan-out. If you have reconvergent fan-out, then this type of analysis becomes harder. If we apply, let us say, here we have inputs A, B, C, D, and let us assume that we have a 1 here, a 0 here, and a 0 here. And let us assume that we have a D coming here. And remember, D is normally 1. Right? According to definition. If you have a D here, then here we have a D and here we have a D bar. And a 0, 0, 0, so this is a 1. So here we have a D. So notice that we have this sensitized path. And on this sensitized path, if you have this is normally a 1, so you will test for a stuck at 0 here. And you will test for a stuck at 1 here. This is normally 0, and in case of a fault 1. And you will test for a stuck at 0 here. So along a sensitized path, you are going to test for half of the stuck faults. Because remember, you have a sensitized path here. So if this is stuck at 0, that would be tested. Or if this is stuck at 1, this would be tested. Or if this is stuck at 0, this would be tested, right? So this shows a single fault can test for multiple faults. Single test can, so here, the vector 1100 tests for several stuck at faults. This observation we can use for test generation. There was a test generation approach. It was called critical path tracing. Basically, I generalize what I have said here. You can do it. I'm assuming here that there is no reconvergent fan out, so there are no lines which are fanning out and then converging like this, because they will cause some complications. There are people who have developed methods for those also, but we are going to not worry about those and consider this situation here. Okay, let us see what happens. So normally this is a 1, so this is 0, and this is 0, so this is a 1, and hence this is a 0, so this is a 0, so this is a 1. And let us give the line some names for convenience. How about I call this line G, and let me call this line E, let me call this line F, and let me call these lines A, B, C, and D. And let us identify all the values which are critical. So if the critical value changes, the output will change. If this one changes, then output will change, right? So we can call this we can say this is a critical value. Consider this one here. If this one gets changed, will it cause a difference? What do you think? Now if this one changes, it is not going to make any difference, right? Because this is already 0, so this is not going to make a difference. What if this 0 changes to a 1? That will cause the output to change, right? Because this is 1 and this is 1, so this would be 1 and hence this would switch. So we can say that this 0 is critical. And now let us look at this line here. And now this 0 is critical, that means possibly these could be critical. Okay, what about this one here? If this 1 changes to a 0, will it make a difference? If this changes to a 0, then this would be a 0, this would become a 1. So we can say this is critical, and we can say this is critical, right? So here we have critical nodes. And of course they are critical under the pattern 1100. They include A, B, C, and G. These nodes are critical, right? And you will notice that this means 1100 will test for